Welcome to the topic 1.5.1D Stack Frame Analysis Animation. In the previous session, we saw how the compiler generates prologue and epilogue, which are instrumental in preparing for a stack frame and unwinding of a stack frame. Also, we saw the body of the code, how it generates the relative address to access data from a stack frame. Also, pictorial representation of the stack frame using only stack pointer as well as using both base pointer as well as stack pointer. In this session, we will see how the very prologue creates a stack frame and epilogue unwinds the stack frame through animation. The acrobatics of movement of values from the processor registers to the stack memory, the push operation, the pushing of values from the processor register to the stack memory, as well as the pop operation, moving of values from the stack memory to the processor register or within the stack memory. All these animation of acrobatics we will be seeing in this video. We wish you will be with us in this journey of learning. So to do that, please do subscribe to our channel. More than subscription, after that you have to ring this bell for you to get continuous notifications from us, right? To continue with, we shall look into the example where the compiler just uses ESP, right? The same example what we had looked in our previous session. We have a prologue part here and the epilogue, right? And the corresponding instructions. We will exactly see in the next slide how the execution of this instruction will create a stack frame, as well as the execution of these instructions unwinds the stack frame. As well as you see, we will see exactly what happens when call is executed, and also we see how the value is pushed from one memory location to into the stack, as well as we see how the value is being pushed from the register to the stack, and also direct values, how they are pushed into the stack, right? All these things we will be looking into the animation part. Here is the much awaited animation part. For our reference, we have also placed this uh, instructions or operations for call and return, right? Now, to give an introduction for this context, this is the CPU holding the registers. For the benefit of brevity, I have only showed ESP and EIP, right? Now, ESP is holding 992. That means the current stack pointer is at the address 992, and the EIP is at 298. Again, for the benefit of brevity, we have changed the addresses here, right? What was there in the previous slide, but the rest of the instructions remains the same, right? It will be easy for us to comprehend. So now please remember, ESP is 992 and EIP is 298, right? Always the EIP instruction pointer or the program counter will hold the address of the next instruction, right? The next instruction to be executed is call 400. So what happens is, when this instruction is executed, there is an immediate transfer of execution from the calling function, that is from the main, to the called function, that is F1. So that means the execution control has to jump towards this, right? When prior to jumping, it has to store the return address into the stack. We will see how that happens now. So the next instruction is executed, right? The EIP is incremented first, and then the next EIP is stored into the stacks. Here the stack pointer is pushed down 988. Here 988, right? Every execution of instruction EIP will be incremented, right? Now the next instruction is 400. This is where the stack frame is created. See, stack value is decremented and the stack frame is created. Now move uh, this value to EDX, right? Again, for the reasons of brevity, we have not shown these operations. That means we will just logically see what's happening here. 14 plus ESP, so 972 plus 14 in hex, decimal uh, 14 in decimal is 20. 972 plus 20 is 992, right? This value is moved to EDX. Again 972 plus 18 is 24, 996, right? 972 plus 24 is 996. This value is moved to EAX and addition will take place, right? We will see all those things now. Please focus on EIP, right? That means EIP is 402, 401 is executed, which we have not shown. EIP is 403, 402 is executed now, which we have not shown. EIP is 404, 403 has been executed, which we have not shown. The next instruction to be executed is 404, which we will be seeing now. The resultant value 9 will be moved to ESP plus 6. What is ESP? 972 plus C is 12. 984th location, the value is moved. Now see here, EIP is incremented. Now this value is moved, right? Now the function is preparing for the execution of the next function, right? So we are passing parameters 9, 8 as well as uh, the resultant uh, or 9, 8 and the value which is there at this location. See, 405 will be executed now. Before that EIP will be incremented. Now ESP is decremented, ESP is pushed because you are pushing the value here, right? Again, next instruction 8 is pushed down, EIP is incremented, ESP is decremented, and 8 is being pushed. Again, next instruction is 407, push L, ESP is now 964 plus 14 is 20, 984. This value will be moved here. See, EIP will be incremented, ESP will be decremented, and how it moves here. That's beautiful, right? Now call instruction is executed. We have seen call instruction. What happens? The next instruction is moved into the stack now. See, 409 EIP will be incremented and that is moved into the stack as usual. So now it is all ready to prepare for the next stack frame execution. Comes here, this stack frame nothing more here. 0 is moved into EAX, which we have not shown, right? The next instruction to be executed is return value. What will return value do? Pop EIP. So the stack pointer is now 956. You pop this value to EIP. Just come back. That is beautiful. We have come back to the hold function, or right, or calling function. So now again the execution resumes here. What happens here? You are adding C to ESP, that is unwinding of stack frame is taking place now, right? Now this is 960 plus 12 is 972. We are again coming back to our stack frame, right, of F1. So this is a stack frame of F1, right? Okay. Now what next we are doing? We are moving the value ESP plus C to EAX. Okay, this I think we will not show. Basically 972 plus, I think this is the result which we are storing in the EAX. Always the return value will be stored in the EAX prior to the exit of the function, right? 972 plus C is 984. This resultant value will be stored in the EAX for the next function to pick up, right? That we are not showing. Now the next instruction will be E411, add 10 to ESP. This is what the complementary action, right? We are unwinding the stack now. This is where the stack pointer is now. The last instruction is read. Return value, what it will do, pop this value into EIP. So see, stack pointer is incremented, the value is popped up to EIP. That finishes our execution of uh, function F1 unwinding of stack frame. Now we are back to our original uh, function main and its stack frame. This was where we started, right? If you remember, and all the values of the stack frame what we had used will be retained in the memory itself. It will not be cleared on unwinding of stack frame. That is the reason any function, suppose next function, suppose main invokes f2. If in f2, if you have not initialized any local variable, the default values will be all these values, which will be called junk values for that function because it is irrelevant for that function. Always ensure that you will initialize the values of a local variable prior to its usage, right? So now we will continue with the next example where the compiler will be using EBP and ESP, right? Yes. Now the same example we are continuing what we had shown in the previous video. The compiler using EBP and ESP both to prepare for the stack frame. This is the prologue part, this is the epilogue part. You have one extra instruction called leave instruction. We will see what it does. Call again, it is the same as what we saw in the previous slide, but leave is the one which will help in unwinding the stack frame. Move the current EBP to ESP, that is the stack is unwinded, and then pop EBP, and the return instruction will do exactly what we have seen in the previous slide, right? Now let us start with the animation part. Now the current values are EBP holds 1000, that is the start of the frame, ESP 992, that is the end of the frame, and EIP, the next instruction to execute, is call instruction. I want the viewers to remember this state, right? Because when the call to the function f1 completes, we have to come back to the same state, right? um, to have a reference for call, leave, and return instruction, we have this reference box. Now we execute call, right? There's a transfer. What does it do? Push EIP. That means this okay, when this instruction is executed, the EIP is 202, it has to be pushed into the stack, and then move operand, that is operand is 400 to EIP, so that it continues in the next instruction will be fetched from this address. Okay, now call, EIP is increased, right? Now what should happen? This EIP should move here. There you go, stack pointer decremented. Now this operand is moved to EIP, right? Now the next instruction is fetched from this address, that is there is an immediate jump of the execution control from the calling function to the called function, right? Now this instruction is executed. Now the previous stack frame start address is saved. See here, this value is moved here. Beautiful. Okay, now Move ESP to EBP. The current ESP will be the start address of this frame, right? We are moving this to here. So before execution of any instruction, we should see the EIP automatically incremented. Now next is subtract 10 from ESP. 10 is 16, 984 minus 16 is 968. So yes, stack frame is created here. This will be the new stack frame, right? Now we have to move EBP plus 8 to EDX. What is EBP 984 plus 8 992? This to EDX. Again, because of brevity of space, we are not showing this operations because we are not representing these registers in the CPU. So we assume that will happen. And the next instruction also we assume it will happen. These two values are moved to the registers EDX and EAX. And next also will execute. Fine. Now the resultant EAX, now 406 is EIP. The resultant EAX is moved to EBP minus 4. EBP is 984 minus 4. 9 at the address 980. The EAX value is moved. EAX should be 4 plus 5 9. There you go. Right now we are preparing for execution of the or next function or invocation of the next function. Push 9 into the stack. Now see here, the value is pushed here, ESP decremented, EIP incremented. Again, right? Push 8, push L, EBP minus 4 to here. See this value we are moving here. There you go. Yes. Call. Again, call is invoked, and I assume we do it automatically without going into that. Now this instruction will be executed. When this instruction is executed, add C to ESP. That is, we are unwinding this stack frame, right? The invoked stack frame, the invoked functions stack frame. We come back again here, right? Now we move the value 0 to EAX. That is the result what we are passing. We are not showing that. Now 413 is the EIP. See, let us see what will happen here. Move EBP. The value of EBP is what? 984 to ESP. That means we are unwinding the stack frame. See here how beautiful it happens. Yes, we have unwounded the stack frame and pop EBP. Now EBP ESP. We have returned back to the stack frame is returned back to the previous function's stack frame. Only thing is the execution control is still here, right? Return value or return instruction. What will that do? Now to bring back the execution control back to the calling function, we have to pop. Now exactly we have returned back to the previous functions stack frame. If you remember the initial state, if you remember the initial state where we started, this is what we had, right? And we are there now. So again, as we discussed in the previous slide, all these values will remain as it is. When the stack is unwinded, the values are not cleared. Hence, the next function when you invoke and when if you have any uninitialized local variables, try to print the values of that. You will see some junk values. Junk because those values are not relevant to that function but was relevant uh, in some other functions. Hence you see it as junk value. Always take it as thumb rule to initialize the local variable to 0 or any designated value for you to avoid getting any surprises in the form of junk values, right? I hope you have understood clearly the dynamics of stack frame creation as well as unwinding of stack frame as well as how a function call is invoked all these things programmer cannot see, only we can visualize. So our attempt in helping the programmer ease out his or her visualization, right, is a result of this animation. This the programmer can see by doing objdump, but this the way the CPU works, right, is all visualization, right. Next, now with all this understanding, we want you to analyze this stack operations for recursive function. For example, factorial of a number n. Try to analyze this factorial of a number 5. See how on paper, see how a stack for you build a stack frame for all the functions and see how it unwinds. That will be a testimonial for your understanding of the stack operations, right. Next, now for the interest of embedded system engineers, embedded system programmers, right, why always during the boot up code, boot initialization, always it starts with assembly code? Why not C code? For a C program to execute, minimum thing should be that stack pointer should be initialized. Without stack pointer, the processor cannot have control of the program. With just the program counter and stack pointer, the processor will have complete control of C program, right? At the start of the very first instruction, you can have a value in the program counter or EIP to fetch the instruction uh, from the address. The first address is called power on reset address, right? So from this address we can make it fetch the instructions, but we cannot have initialize the stack pointer. Hence, initial few instructions during the boot up code should be assembly instructions. As part of assembly instructions, we initialize the stack pointer and jump to the C code. Henceforth, right, C execution can take place. That is, the instructions related to the C program can execute. I just thought this could be a right context to introduce this idea of boot initialization in an embedded system, right? Next, as usual, this is the OS we have used. It is Ubuntu 16.04 on i386 GCC version 531. All right. What next? Next topic will be also interesting. It's on stack smashing. People would have heard, you would have heard about stack smashing. We will see with an example what is stack smashing, what is the compiler's uh, provision in helping the programmers uh, in preventing the errors in the program, right. For that, I would want you to analyze this program where we have initialized an array within a function, right, and also assigned a value to a array variable, right. We have assigned a value to an array index. Now we have declared an array outside a function global array, and we have assigned a value into an array index, right. Executed this, we have no issues. And also we want you to analyze this program, right. More details, this is just a preface of what we will be discussing in our next session, right. If you have any questions, any doubts, comments, feedback, please feel free to post all these things in the same video page of in this current video page, right? Till we see you in the next session, take care and bye bye.